All right, so our next set of questions is to go over the calculated wavelength, exceptions to electron configuration, and dealing with atomic radius, and then it's exam questions after that. So going over how to calculate wavelength. So I'm going to go ahead and assume that you're asking for the most complicated wavelength calculation that we have, which is the one that would sound something like this. What is the wavelength in nanometers of a photon released when an electron moves from n equals 3 to n equals 1? And I personally think of this as being the most complicated because it has the most steps involved. So first of all, we are going to get to nanometers, but the only numbers we're given is this stuff, n equals 3 to n equals 1. So I do like to consider and think through the fact that this is n equals 3, and we're starting here, and we're moving down to n equals 1, and that's where we're landing. So that means that this is going to be my initial, and n equals 1 is going to be my final. Now, I'm going to use your potentially useful information page. Whoops, but that's not what I was looking at last. I might need that later. I need your potentially useful information because I'm going to show you how to use the equations that are on here. So one of the equations that you have on here is this thing with E. So we're going to be using energy a couple different ways, but we're going to use this negative bz squared n squared. I should have done one more thing. This is the bad thing with me. Should say in a hydrogen atom to use that equation properly. So we have E equals negative bz squared divided by n squared. In here, B is a constant. We're going to go back to that potentially useful information page to grab that later. Z is my atomic number. Really, this is technically my nuclear charge. N is my energy level. But you might be saying, we have 2 energy levels, but we only have 1 energy. That's because when our wavelength, in order to calculate the wavelength of a single photon from this change, I need to calculate the change in energy. When I calculate the change in energy, this is going to be the difference between these. So this is going to be negative bz squared divided by n squared final minus negative bz squared divided by n squared initial. I'm going to clean this up a little bit as I copy this down. So first of all, my nuclear charge. I have this as a different page. My nuclear charge, when I look at a periodic table, I know we had a discussion about memorizing things. We're going to probably do a different periodic table, or it'll have to say H. So here's my hydrogen, top left. I know I've scribbled all over this a couple times by now, but there is a 1 right above it. So that's my nuclear charge, is that 1. So therefore, when I come back over here to clean up, I'm going to do a couple things. I'm going to take B out so I can deal with like my constant last. Negative Z is going to be 1 squared. My final is n equals 1 minus a negative, turns that to positive. My B I've already taken out. Z squared here is 1 again. Initial is 3 squared. So now I have B times negative 1 squared divided by 1 squared is just 1. Plus 1 squared is 1 divided by 3 squared, which is 9. So this is B times negative 8/9. You can also plug that into your calculator. Then I really like the value of B. So I'm going to come back to my potentially useful information page. And B is the constant for the Bohr model of the hydrogen atom right here, 2.180 times 10 to the negative 18th joules. So 2.180 times 10 to the negative 18th joules times negative 8/9. So that does get me a number for my change in energy. So that's what this is. This is my change in energy. Now that I have this, I want wavelength. So I'm going to take a look back at my equations, and we have an equation that is going to be able to go from energy to frequency, and an equation that can go from frequency to wavelength. Some of y'all may have memorized the combination of these two, or you may want to take the algebra steps to combine them. You are welcome to do that. I'm not going to, mostly because I don't have to. The one thing I will say though, as I move from one of these to the other, my frequency has to be a positive value. So even though my change in energy does have this negative sign in it, I'm basically going to take the absolute value because my frequency has to be a positive number. So frequency has to be positive. So as I write everything out, that's the thing that I'm expecting to see is a positive number in the end. Yes, I did do Planck's constant from memory. This h here is the same thing as this h up here. So that is that number and value. This is one of those games where I've just been teaching a long time. So I have some of these numbers memorized. You don't have to memorize them. They're hanging out back on that potentially useful information page. And then again, we're going to do one more calculation. Again, you don't have to have that memorized. It's right here. C equals wavelength times nu, which is the frequency. C is the speed of light. You do need to know that's the speed of light, but there's a little letter C right there. So one thing that I will say as I'm doing this is there are a lot of things on that potentially useful information page, and it's your job to know how to use them. You do need to practice. Just because it's all there for you and therefore there's less memorization required, you still need to know where things are and how to use them so that you can do them in the amount of time required. I get 1.025 times 10 to the negative 7th, and that's going to be in meters. So therefore, I want this in nanometers, I believe, nanometers. So 1.025 times 10 to the negative 7th. And there's 1 times 10 to the negative 9 meters in 1 nanometer, which gets me 102.5 nanometers. So hopefully that helps out with wavelength calculations. So we actually started with values of N and went to wavelength. So that's a couple different ways you might be given wavelength and asked to solve for it. Next up, exceptions to electron configuration. So hanging out in notes somewhere. Is it? There we go. So there are 5 elements that you're responsible for their exceptions. So typically when we talk about electron configuration, most things we are going to assume just go from left to right across the periodic table. In reality, there actually are more exceptions than that, but we are just going to assume that there are only 5 exceptions. And the 5 exceptions we're going to ask you to know about are chromium, molybdenum, so Cr, Mo, and then copper, silver, and gold, Cu, Ag, and Au. So those are the 5 that you are responsible for their exceptions. So what makes these things exceptional? These things are going to be exceptional because they're going to do something really weird. Let's just focus on the shorthand notation for a moment. So when we're trying to get to chromium, we could go through all the different values of N, but there's a shorthand notation where we just use the most recent noble gas. So we're going to start with argon. And then I would originally go for S2 and then 1, 2, 3, 4, 3D4. But that's not what actually happens because the 3D subshell is almost full. at this point. So what actually happens is we're actually going to borrow an electron from the 4s and move it to the 3d. This half-filled subshell makes this exception much more stable because essentially you're going to have 5 electrons all at a lower energy. Remember, lower energy means more stable. So my actual real electron configuration for chromium is 4s1 3d5, having this half-filled subshell. So that is how that works. So that's one of your exceptions. Molybdenum is right beneath it. So molybdenum is going to follow that same pattern, except molybdenum this time would be krypton. So this one was for chromium. So I'm going to move to red. So molybdenum would be krypton in brackets, and then 5s1 4d5 for molybdenum. Similarly, when we talk about copper, over here, copper should be the same argon base, and then we're still going to be borrowing one from S, but that's so that we can have 3d10. So copper would originally have 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons in its d subshell, but having a full d subshell is even more stable than a half-filled d subshell. So therefore, it's going to borrow an electron from the 4s as well. And you'll see again, the same idea with silver and the same idea with gold. So this is a game that's all about stability. So these exceptions are in fact all to talk about how stable can this be, and where are we going to get that extra stability from. And borrowing an electron out of 4s, where there's only 2 electrons, will make this whole thing more stable. So you're responsible for those 5. Cr, Mo, Cu, Ag, Au. Atomic radius. So the only thing with atomic radius that I think sometimes gets a little strange is when we do ionization energy and electron affinity, we point basically to helium and we go more. Now we point to helium and we go small. So for radius, small things are going to be over here, large things are going to be over here. Now some of this though should make sense. When we talk about values of n, the larger my value of n, the larger my atom. The larger my value of n, the farther away from the nucleus that outermost electron is. So as you go down the periodic table, you should expect these to get bigger as you go down. So that general effect should make sense. So as you go down, you should expect your atom sizes to increase. Now, as far as left to right goes, this one's a little bit stranger, but when you think about it, realize that if we're talking about something in, say, the 2p subshell, so I have a nucleus, and then I have electrons in n equals 1, and I have electrons in n equals 2. What's happening here is as I'm going from, say, carbon to oxygen to nitrogen, I have 6 protons, and then I have 7, no, I cut oxygen. I don't know why my brain wants to switch oxygen and nitrogen. Nitrogen has 7 protons. Oxygen has 8 protons. So yes, these are also gaining electrons. So I'm going to have 2 electrons in n equals 1 here. I have 4 electrons here. 2 electrons here, 5 electrons here, and I'm supposed to make that look smaller. 2 electrons here, 6 electrons here. So while yes, I know that we're also gaining in electrons, what we're also gaining is more positive charge. And since this is still that n equals 2 shell, or I could even think about my p subshell that some of those electrons are hanging out in, realize that those are all then of equal energy. So I've got more positive charge to hang on to my electrons. So as I go across the periodic table, I simply have more positive stuff to hang on to the electrons. So I wind up with a smaller atom because it's also a little bit denser because of that ability of the nucleus to hold on to the electrons. So as I go from left to right, I should actually see these things becoming smaller. So left to right is smaller, up to down is bigger. So however you want to think about this is up to you, but atomic radius, just realize that we are trying to talk about the size of the electrons, and our values of n, or sometimes our values of n versus our protons, is what's going to affect that. And now I get to move on to all of the exam questions. So for those of you that did not want to know how to do certain exam questions, this is the time for you to shut down the video, because that's all I have left now is dealing with old exam questions. These are all going to be from fall 22. This one says identify the group number of element X, which has the following successive ionization energies. So this is the first ionization energy, the second, the third, the fourth, the fifth, the sixth, etc. What you're looking for here is you're looking for a big jump. And actually, Alex will have a thing on there. And in Alex, what they're going to do is they're going to do like 580 and then 1800 and then 27 and then 11,000 and then 14,000 and then 18,000 and then 23,000 and then 27,000 and then 31,000. Somewhere in there, though, there should be a really big gap, because if you look at the differences in between here, this is a difference of about 1,000. This is a difference of about 900, but that's 2,000. This is a difference of about 8,000. This is a difference of 3,000. This is a difference of about 3,000. This is a difference of about 5,000. 23 and 27, that's about 4,000. 27 to 31, that's about 5,000. So somewhere there is a biggest gap right there, which means that as we're going along, first, second, third, fourth, it's the fourth one where suddenly there's a big jump. What this is going to translate to in ionization energy is that these are actually going to be what we refer to as my valence electrons. So what's happening here is as I'm removing electrons, this is suddenly where we get to the core. So for valence and core, what we're trying to talk about is if I was talking about something like beryllium, 1s, 2s. My highest value of n is what we refer to as valence, because this has the highest value of n. Therefore, these are what we would refer to as my core electrons. It's always easier to get rid of the valence electrons than the core electrons, because again, that when we're talking about even that size we were dealing with earlier, oh no, I lost my pretty graphs, my pretty drawings. Maybe they're not so pretty. Realize that the farther away the electrons are, the easier they're going to be to remove. When you go into that next value of n, you should see a jump in ionization energy because you're getting closer to the nucleus. It's more difficult to remove those electrons. So whenever you see that jump in the energy of ionization energy, what you're really seeing here is where our core electrons are. You're seeing that you finally moved in here. So beryllium, for example, has 2 valence electrons. So this, however, had 3 valence electrons. So I'm looking for something that has a core of whatever, and then would go 1, 2, and has another one. So I'm looking for something that has 3 valence electrons. In our periodic table, my 3, I'm sorry, I know I write all over this, but every time I look at it, I'm like, how am I supposed to see anything when I have written so much? So 3 valence electrons is going to be this third group. So as we go across 1 valence electron, 2 valence electrons, 3 valence electrons. So my group 3A is going to be what this is. 3A. Next up, consider the transition from n equals 5 to n equals 1 orbit in the Bohr model of the hydrogen atom. Which of the following statements is true? Okay, so I'm going from n equals 5, 1, 2, 3, 4, 5 to 1. So I go from high to low. Energy is absorbed. Nope. Things should be released here or emitted. So emitted is right. So both of these are fine, but the absorbed ones are wrong. Not either emitted or absorbed. So I only have two options. I've got B and D, resulting in the atom being in an excited state versus the ground state. Well, over here, n equals 5 is a high energy state. So this is excited. Down here with n equals 1, this is the ground state. So then the question is, which way is this going? And since this goes from 5 to 1, this is now going to be in the ground state by the time that we're all done. So that means that D is the correct answer. For those of you who are curious, I'm going off of the list that was given to me out of the chat from the exam review last night. That's where these are coming from. Which element's neutral ground state electron configuration is best described by? So a lot of this is written out, but we're going to try to find, so here is just n equals 1. Lovely. Here's n equals 2, 3s, 3p. That's 3, 4s, 3d, 4p. That's 4. 5s, 4d, 5p. That's 5. 6s, like at the end. 6s, 4f, 5d, 6p. So here's, actually not all of those are valence. The only valence ones are the highest value of n. So just for the record, the 6 parts are my valence electrons. So when I'm looking at the periodic table, which at this point I'm going to need to copy this and move it. Boom. Where is it? So what I need to do is, so this covered everything in n equals 1 and everything in n equals 2 and 3 and 4 and 5, and 6 is then where we basically start. So I get to 6s2, but I keep going, so it's not barium. And then I hop into the 4f, but this is 4f14, so it's not actually any of those. Then I go all the way through 5d10, it's not any of these. And 6p3, 1, 2, 3. So that then is where I stop, because it's the third element in the p block. That is this guy right here. That's bismuth, by the way, but Bi. So 6p3 is really the part I needed. So I'm in the p block and the third element from left to right. There we go. So that was me realizing these are too small for you to figure out which one's next. 24, 26, 28, and 30. Oh, third electron affinity. So we didn't do electron affinity during the exam review. We did ionization energy, but one of these things is still true. So we talked about ionization energy. We talked about the fact that wherever you left off is wherever you pick up again. Electron affinity is going to be the same, where we start off with an atom and we are adding electrons. So this is going to get negative as we progress. So my first electron affinity looks like this. My second one, we start with wherever we left off. So this is like a sequel movie where wherever we had before is where we begin. And then my third one is still going to start off with this guy. And we're going to add an electron to get a 3. And they were actually nice to you guys on this one, and all of these are in the gas state, because these also should all be in the gas state. So for the third electron affinity, I'm looking for something that starts with -2 and ends with -3, and that is this one. I can get rid of all the positive ones because that's ionization energy. I just need my electron affinity, where I'm adding electrons onto these one by one. You also might notice that I didn't actually go through all the answer choices in this case. Since that's the third electron affinity, I just wrote them all out and then matched it. You may also find that this is the easier way to do these things, because if you have to try to mentally think through all 5 answer choices, sometimes you start to look really good. But if you do the work separately and then match it, a lot of times it's more straightforward what's the correct answer, because you've already decided. You already decided what the correct answer was, and now you're just looking to match it. That's 30. I don't want 30 yet. I don't want 30 yet. I want 28 first. 28. Ultimately, the Bohr model was abandoned because it proved to be incorrect, which the following statements is true concerning the Bohr model. Anything that has to do with a wave is wrong, because Bohr didn't know about waves. So Bohr thought particles, basically, particle only. So anytime we see the word wave associated with the Bohr model, it's wrong. It violated the law of conservation of mass. No. We will violate the law of conservation of mass later, but that's nuclear. Also, it's going to become the law of conservation of mass and energy. But anyway, that's not right now. It provided no explanation for the line spectra. Also wrong. Explaining the line spectra, this is what it did. This is what Bohr actually succeeded in doing, was providing the explanation for the line spectra. It only worked for the hydrogen atom. It did not work for any other neutral atom in the periodic table. Yes, that's what the problem is. It did work for hydrogen. It explained hydrogen's line spectra, but only hydrogen's line spectra. Consistent with the uncertainty principle, also no, because that was another wave idea. So D, answer is D. So this is the part where you do need to know which was Bohr versus Schrodinger and what all those pieces and parts are. Now, the last question has a key already written out for it, and I'm a little nervous because I wrote the key for this problem last year. So I'm totally fine that you want me to talk through it. I'm frankly just nervous because if you didn't understand the key, I don't know that me talking through this is going to help you, but we're going to try anyway. But I got to fess up. I'm the one that wrote the key for this in that fall 22 exam. So it's my fault. I typed that up. Okay, so this is asking what's the wavelength of light in nanometers emitted when an electron moves from E4 to E3. So we are dealing with E4 to E1. Did I say E3? E1. I'll make these things match. Consider the following energy levels of specific orbits in a hypothetical atom. What's the wavelength of light emitted? So this is actually going to be very similar to what we did, the very first one I did in this video, where we were looking at that change in energy. The difference is that when we did the change of energy before, we did this negative bz squared n squared minus negative bz squared n squared. The thing is that we don't have to do this, because this is if you were given the energy levels. These are already in joules, so I don't need any of this. What I need is I just need that change part, where we're going to go final minus initial. This says I move from E4 to E1, so I'm going from here down to there. So therefore, I should have my final is negative 15 times 10 to the negative 19th minus negative 1 times 10 to the negative 19. These are all in joules. So that's basically negative 15 times 10 to the negative 19 plus 1 times 10 to the negative 19. So that should just be equal to negative 14 times the negative 19. I'm going to grab the key real quick. I meant to actually do that as we went along to show you guys that we're chugging right along. So for our key, that's what we did. It does show on here that you either could have done what I did, which is 14 times to the negative 19 or 1.4 times to the negative 18. I know for a lot of you, I've had some conversations that you're like, but this is incorrect scientific notation. And I do agree with you, it is. But frankly, since that's what was used up here, I didn't write this question. I just wrote the key. I would never have done that. It doesn't matter. Sorry. Sudden moment of realization. I would have rewritten the scientific notation. So anyway, both of those would have been correct. You also do need the sign on here. And then to get wavelength, remember last year we actually had them memorize their equations. Or again, some people might have had this one memorized, or they might have done it individually. So this then becomes the same general walkthrough of mathematics that we did on the very first problem. So since the key is here with the equations, and since I did already walk through how to go from energy to wavelength in the very first question that I did on this part of the video, I don't know how many parts of videos we have now. I'm actually not going to do the rest of this. So if you're having problems on this part where we're taking the change in energy and moving to a wavelength, odds are really good you're having problems with your calculator. So I would encourage you to practice with your calculator. Take that either to the tutoring center or the chemistry clinic or various other, whatever you've got, me also, and figure out what's going wrong with your calculator. Because if you're having problems going from here to the end, it's likely a calculator problem. Okay, those are all the questions that I'm aware of. So we're going to stop this. Good luck.